Good morning to all of you. My name is Vishal Jaiswal. I am assistant professor in Department of Computer Science and Engineering, Ajay Kumar Garg, Engineering College, Ghaziabad. Here I am going to take lecture on in computer organization and architecture, and my current topic that I explained, that is associative memory. It is also known as the content addressable memory, that is called CAM. If we talk about content addressable memory, the time required to find an item stored in memory can be reduced if stored data can be identified for access by the content of the data itself rather than by an address. Basically, in content addressable memory, we access the data not by the address but by the content. We can also call this data. A memory unit accessed by content is called an associative memory or content addressable memory. This is the basic definition of content addressable memory, and this type of memory is accessed simultaneously and in parallel on the basis of data content rather than by a specific address or location. If we talk about reading or writing a word, and when a word is written in an associative memory, no address is given. The memory is capable of finding an empty unused location to store the word. Basically, memory is capable to search the empty location for the right operation, and when a word is to be read from an associative memory, the content of the word or part of the word is specified. The memory locates all words which matches the specified content and mark them for reading. Because of its organization, the associative memory is uniquely suited to do parallel searches by data association. Moreover, searches can be done on an entire word or on a specific field with a word. And associative memory is more expensive than random access memory because each cell must have storage capability as well as logic circuit for matching its content with an external argument. Basically, content addressable memory is differentiate from random access memory in the sense that the random access memory has the storage capability, but the content addressable memory having the capability of storage capability as well as the logic circuit for matching. This logic circuit of matching differentiate from the random access memory and makes it more efficient or more highly effective in case of memory. This is the block diagram of associative memory. Here we can see that here we have an argument, that is A, argument register, that is A, and we have a key register, that is K. We have an argument register. What we need to search, we place it in the argument register, and what basis we have to search, we place it in the key register. Then we have a associative memory and logic that contains m words and n bits per word, and here two operations are performed, that means read or write. And if argument register in key argument register, content of argument register is matches on the basis of key register, and if there is a match, then the corresponding match entry is marked in match register. This is the block diagram of associative memory. The block diagram of associative memory is shown in figure, that is in previous slide, and it consists of a memory array and logic of m words with n bits per word. The argument register capital A and key register capital K each have n bits, one for each bit of a word. The match register M has m bits, one for each memory word, and each word in memory is compared in parallel with the content of an argument register. The word that matches the bits of the argument register set a corresponding bit in the match register. After the matching process, those bits in the match register that have been set indicate the fact that their corresponding words have been matched, and reading is accomplished by sequential access to memory for those words whose corresponding bits in the match register have been set. The key register provides a mask for choosing a particular field or key in the argument word. The entire argument in the is compared with each memory word if the key registers contains all ones, and otherwise only those bits in the argument register that have ones in their corresponding position of the key register are compared. Thus, the key provides a mask or identifying piece of information which specifies how the reference to memory is made. This is the example of an associative memory. Here, suppose that we have an argument register A and a key register K have the bits configuration shown below, and only the three leftmost bits of A are compared with the memory words because K has ones in these positions. This is the example of associative memory. Here we have an argument register A that contains the value that is 101 and 4 times ones then 00, and we have a key register that is K which has the values continuous 3 times 1 then 6 times zeros. This is the key register, and we have two words, that is word 1 and word 2. And if we talk about associative memory, then on the basis of key, because on the basis of key here these are the three ones, so we have to search corresponding to key register, and we have to match 101 at this position. Sorry, here at this point, that is 111, there is corresponding bits is 100, which is not matched with 101. So word 1 is not matched. And if we talk about word 2, and word 2, if we talk about word 2, then corresponding 1 is matched with 1, corresponding for this one, this 0 corresponding match with 0, and corresponding this one match 1. So we can say that word 2 is matched and word 1 is not matched. Basically, this is the example of associative memory. Here we have an argument register and key register. On the basis of key register, we have to search a particular word that is matched with key register or not. Word 2 matches the unmasked argument field because the three leftmost bits of the argument register and the word are equal. This is the associative memory of m words and n cells per word. Basically, here the further division of argument register, that is A1, AJ to AN, and we have a key register K1, KJ and KN. Basically, these are the bits of the argument register, these are the bits of argument register, and these are the bits of key register. We have to match the content of argument register in these words, word 1 to word M. When a particular word is matched, let's suppose this word is matched on the basis of key register, then the value of this is set to 1. Let's suppose this word 1 is not matched with key register, then the value of this is 0. And let's suppose this value of word is matched with key register, argument register, then value is set to 1. So we can say that these two words are ready for reading, and these are matched with argument register on the basis of key register. Then the application of cache associative memory is in cache mapping techniques. So if we talk about cache mapping, the role of associative memory is important. So here we can also discuss the cache mapping techniques, and there is one part it is covered in this lecture, that is associative mapping. The performance of a cache memory is frequently measured in terms of a quantity called hit ratio. When the CPU refers to memory and finds the word in cache, it is said to produce a hit. If the word is not found in the cache, it is said to be it is in main memory and it counts a miss. The ratio of number of hits divided by the total CPU references to memory, that is hit plus miss, is the hit ratio. There are three techniques for cache mapping. First one is associative mapping, then direct mapping, then set associative mapping. But here our limitation is that we have to only discuss the associative mapping, because in associative mapping the concept of associative memory is used. So we have only discussed this mapping, that is called associative mapping. For before discussing the associative mapping, we have a certain scenario in which we can discuss the associative mapping, and the scenario is the main memory can store 32K words of 12 bits each. The cache is capable of storing 512 of these words at any given time, and the CPU communicates with both memories, and it first sends a 15-bit address to cache. If there is a hit, the CPU accept the 12-bit data from the cache, and if there is a miss, the CPU reads the word from main memory, and the word is then transferred to the cache. This is the architecture of this scenario. The scenario is, our main memory is 32K cross 12. It means we have in main memory we have 32K words, and each word having of 12 bits, and our cache memory is 512 cross 12. It means our cache memory is having 512 words and each word having of 12 bits, and we have a one CPU, and when if CPU wants to access some data, then CPU first search it in the cache memory, and if the word is found in the cache memory, then it is called hit, and if the CPU does not find the data in the cache memory, then CPU access the data from the main memory. After miss, CPU access the data from main memory, and one copy of data goes to the cache memory, that is accessed from the main memory. So this is the scenario where main memory is 32K cross 12 and cache memory is 512 cross 12. In associative memory, the fastest and most flexible cache organization uses a associative memory. The associative memory can store both address and content of the memory word. This permits any location in the cache to store any word from the main memory. This is the general architecture for associative cache mapping. Here we can say that our CPU address is of 15-bit address, and this scenario is given in octal numbers, all numbers in octal. It means one number is represented in 3 bits. One number is represented in 3 bits. So the address, for address we have 5 digits. So we can say that this is of 15-bit address. So CPU places the 15-bit address in the argument register, and we see in the associative mapping that we have a key register. Then here we can say that our key register values is of 15-bit and all the bits is 1. This is of 15-bit of key register, and all the bits is 1. The important thing is that the key register values is of 15-bit and all the values of key register is 1. So we can match all the 15 bits to the addresses, and the most important thing of the associative mapping is that these CPU address 15-bit the places in argument register, and argument register contains the address that is a 15-bit is parallel match with all the addresses. This is the most important thing of the associative mapping, that is the parallel matching is performed in this mapping technique. So which address matches the argument register, because the key register value is 15-bit, so we can all matches all 15-bit addresses are matches with this address. Then if suppose this address is matched with the argument register, then corresponding data, that is of 12-bit data, is read from the memory, associative cache memory. This is the reading process, and we can here we can also say that the content, that is address plus data is stored at any location. This is also an important thing in associative memory. We can store address data in pair, and this address data pair is stored at any location of the memory which is unused. So in this way we can perform reading. Let's suppose this address is matched with the argument register, then their corresponding 12-bit data is read by the processor. When CPU write the word into the cache memory, into the associative cache memory, and CPU gives data, then suppose we have all the positions are filled by the data. Let's suppose here we have any data, and if you want to write the data in the associative memory, then associative memory is capable to find the unused location and places the address data pair in the associative memory. But the case is that our associative memory is full. Then this case, what location should be replaced by the new address data pair, that is depend on the replacement policy. We have the 3 policies for replacement. First one is first in first out, second one is LRU, means least recently used, and third is that is optimal. We can use any of these replacement policy to replace the address data pair if our associative memory is full. For the cache designing, associative memory is very costly, so we cannot use associative memory in the cache designing. We used RAM for cache designing, and because associative memory is very expensive because of the logic circuit in their each cell. Thank you for this lecture.